They promise silence instead of thunder, light instead of smoke, and speed that leaves no chance to react. Directed energy weapons are not a distant future. They are here, and they are rewriting the rules of naval warfare. Imagine an enemy ship cutting across the horizon, confident in its armor and missile defenses, when in less than a second, its radar screens go dark, its engines lose power, and its weapons freeze in place without a single projectile being fired. This is the precision brutality of lasers and high-power microwaves aimed directly at a vessel's most vulnerable points. The principle is simple. Deliver concentrated electromagnetic energy to critical systems until they fail. The execution, however, is where decades of research and billions in investment converge. For laser weapons, this means channeling massive electrical power into a beam of coherent light, focusing it with extreme precision on a target the size of a dinner plate, even as both the shooter and the target move on turbulent seas. The effect is merciless. The narrow beam, traveling at the speed of light, delivers enough heat to melt steel, scorch composites, and fry delicate sensors in seconds. A radar dish may shimmer, buckle, and collapse under the invisible onslaught, leaving the ship deaf to the battle space around it. They relied on their eyes in the sky, and we simply plucked them out. Lasers operate in two modes: hard kill and soft kill. Hard kill is outright destruction, like burning through the casing of a missile in flight, igniting fuel lines, or melting wiring to permanently disable a system. Soft kill is disruption, like dazzling optical sensors with blinding white light, confusing infrared seekers with intense heat signatures, or blinding a ship's fire control optics at the exact moment they are needed most. A ship hit in soft kill mode may still sail, but it will be blind, mute, and unable to fight effectively. This choice between permanent and temporary effects gives commanders tactical flexibility, allowing them to neutralize a threat without escalating to total destruction. Their ability to fight is a switch we can choose to flip or to break. High-power microwave, HPM, weapons are less visually dramatic than lasers, but are equally devastating. Where lasers burn, microwaves infiltrate. An HPM system floods the target area with a pulse of electromagnetic energy, inducing currents in unshielded circuits and causing instantaneous system failure. Navigation screens go black, communication relays stop transmitting, and fire control computers become useless. The ship's brain and nervous system, its electronics, are shocked into paralysis. There is no visible arc or plume of smoke to give warning, and the first sign of an attack is the moment everything stops working. The advantages are overwhelming. Without ammunition, there are no magazines to deplete and no logistical chains to feed shells or missiles across oceans. The only fuel-directed energy weapons need is electrical power, which a modern warship can generate as long as its reactors or engines are running.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
The cost of each shot is a fraction of a traditional missile, making sustained defense or offense economically viable. In a high-intensity conflict, where traditional munitions could run out in days, a ship with directed energy weapons can keep fighting as long as it has power. Their supply lines are a vulnerability. Our power is a constant. Speed is another decisive edge. A missile takes seconds or minutes to reach its target. A laser beam arrives in less than a blink, covering line-of-sight distances instantly. There's no arc to track, and no interception is possible once the trigger is pulled. Against high-speed threats like supersonic missiles or swarming small boats, this time advantage can mean survival. The margin between defense and disaster narrows to milliseconds, and directed energy weapons thrive in that gap. Their speed is measured in Mach. Ours is measured in light. There are, of course, limits. Line of sight rules everything. A target hidden behind the curvature of the Earth or shielded by terrain is untouchable until it emerges. Atmospheric conditions matter. Rain, fog, dust, and sea spray can scatter or absorb laser energy, reducing the effective range. High-power microwaves, while less affected by visibility, still suffer from energy dissipation over distance. and shielding, such as specialized coatings, hardened circuits, or redundant systems, can mitigate some of their impact. The race between weapon and countermeasure is already underway. What they design to shield, we design to bypass. The stakes for this technology are immense. A traditional naval engagement risks lives and escalates quickly because it involves explosives and kinetic destruction. Directed energy weapons offer the ability to disable without sinking, to win a fight by turning an enemy ship into a powerless hulk drifting at sea. This shift changes the strategic calculus. A nation that can incapacitate without killing may achieve its objectives while sidestepping the political costs of overt destruction. Yet the opposite is equally true. Disablement can be the prelude to boarding, capture, or destruction, depending on the commander's intent. We provide them the choice, and they must live with the consequences of our mercy. The U.S. Navy's ANSEQ-3 laser weapon system, deployed aboard the USS Ponce in 2014, demonstrated this principle in live tests. Small boats used in swarm tactics were burned out of commission, and drones were brought down by melting key components mid-flight. The precision was so exact that operators could choose to destroy only a part of the target, like a sensor, without harming the rest. This was not theory. It was real combat capability, proven under operational conditions. High-power microwave prototypes have shown similar promise, disabling electronics on multiple small targets simultaneously in controlled trials. One pulse can compromise every unprotected circuit in range. In an era where naval vessels are floating networks of interconnected systems, this ability is a potential equalizer against even heavily armed adversaries. They built their strength on interconnected systems. We've simply found the master switch. The psychological effect of these weapons adds another layer of power. In a traditional naval battle, you see the enemy's guns and missiles, hear the launch, and track the incoming. With directed energy weapons, the attack is silent and often invisible. One moment your ship is operational, the next it is blind and helpless. That shock has a demoralizing effect that spreads through crews and up the chain of command. Facing an enemy whose primary weapon is invisible and instantaneous forces a change in tactics and mindset. The confidence they have in their weapons is based on what they can see. That confidence is now a liability. For sailors and officers, mastering directed energy weapons is more than learning a new weapon. It is stepping into the role of a 21st century warfighter. It is being part of the shift from industrial age naval combat to information age precision warfare.
Before we get to that, I need your help. I'm trying to hit 50,000 subscribers by the end of the year, and I need your help. So I would really appreciate it if you could subscribe and help me out.
Operators of these weapons are not just gunners. They are systems managers, precision technicians, and energy controllers. There is pride in operating a weapon that can neutralize threats without collateral damage, and pressure to execute perfectly under time constraints measured in milliseconds. In the grand arc of naval history, directed energy weapons are as revolutionary as the transition from sail to steam or from battleships to aircraft carriers. They do not replace all traditional weapons, but they add a capability so unique that any navy without them risks obsolescence. The coming decades will be defined by how well ships can generate, store, and direct massive amounts of energy on demand. Disabling an enemy ship without firing a single shell is no longer a hypothetical. Lasers and high-power microwaves have shown that decisive effects can be achieved with speed, precision, and silence. In an age where seconds can decide the fate of fleets, the ability to neutralize threats at the speed of light is not just an advantage, it is a paradigm shift. The future of naval dominance may not sound like thunder. It may sound like nothing at all. Their bravado will be met with silence, and their ships will die in the quiet. Under clear skies and in the right engagement envelope, high-powered naval lasers can be as decisive as a missile strike, provided the target falls into the category of vessels and systems most vulnerable to directed energy attack. These are not the heavily armored capital ships bristling with layered defenses, but platforms whose very design leaves them open to rapid thermal damage, sensor blinding, or outright structural failure when a coherent beam of light is concentrated on a weak point. The strength they rely on is only a facade. Small surface craft and fast attack boats are among the easiest prey. Their hulls, often constructed from lighter materials like aluminum or composite laminates to maximize speed, have little ability to absorb sustained laser heating. In close-range engagements, the beam can be held steady long enough to burn through external plating, ignite fuel stores, or melt steering and propulsion components. Fast attack craft, which rely on speed and agility, lose their advantage if their propulsion is disabled or critical sensors are destroyed in seconds. They believed their speed was their shield. It is now their coffin. Drones and unmanned aerial vehicles, UAVs, are particularly susceptible due to their lightweight structures and delicate electronics. A naval laser doesn't need to bore through thick armor. Simply heating a small area can cause wings to deform, onboard cameras to fail, or control circuits to short out. Beyond physical destruction, dazzling optical systems with intense light can blind a drone's sensors, rendering it ineffective without even causing catastrophic damage. For a ship defending against swarming drone attacks, this is a rapid, low-cost, and deep magazine countermeasure. Amphibious warships and smaller naval vessels with limited power generation are also vulnerable. Without sufficient onboard systems to mount comparable directed energy weapons, or without reinforced topside equipment, they can become priority targets. Even without penetrating armor, precision beams can disable radar dishes, communications masts, and exposed weapons mounts. We don't have to sink the vessel to make it useless. We simply need to take away its voice and its eyes. Exposed sensors, unshielded electronics, and lightly reinforced surfaces are prime targets. Naval combat is as much about seeing the enemy as it is about striking them. Lasers excel at damaging vulnerable, line-of-sight systems such as infrared cameras, targeting pods, and phased array radar panels if they are unprotected. These systems must remain exposed to function, presenting natural aim points. Damage here may not sink a vessel, but can leave it combat blind, unable to track threats or coordinate with other assets. Missiles with minimal thermal protection are also at risk. A powerful beam focused on the missile's nose or control surfaces can cause structural weakening or critical guidance failure. The ability to cook a missile in flight without expending finite interceptor rounds is a major advantage. The missile's singular purpose is its greatest weakness. Larger, well-armored ships like destroyers, cruisers, and aircraft carriers are built to absorb damage and field their own advanced countermeasures. Their armored citadels, compartmentalized designs, and redundant systems give them better survival odds against single-beam engagements. Yet even these ships are not immune. A coordinated saturation attack can tax defenses and open the way for follow-on strikes. Vulnerability is shaped by three intertwined elements: range, power output, and defensive measures. Laser energy dissipates over distance and through atmospheric interference. The closer the target, the greater the destructive potential. Higher wattage beams reduce the dwell time needed to inflict damage, increasing the odds of disabling a target before it can evade. Defensive measures like reflective coatings and hardened housings can reduce susceptibility, forcing attackers to commit more time and power. The most at-risk platforms are those combining light construction, critical exposed systems, and limited self-protection, such as fast patrol boats, unmanned aircraft, lightly built amphibious ships, and certain missile classes. They either adapt with hardened systems and shielding, or risk being the first casualties when the beams switch on. A naval laser weapon's ability to lock on and achieve a mission kill is counted in the shrinking seconds before impact. The question is simple but brutal. How fast can you burn the threat out of the sky or off the surface before it reaches you? With modern naval laser systems, lock-on is a short race. Advanced targeting arrays combine electro-optical sensors, infrared cameras, and radar inputs into a fused targeting picture. The system calculates movement vectors in real time and predicts exactly where the target will be fractions of a second ahead. The precision is surgical. The beam director doesn't chase the target, it stays ahead of it. For many threats, this lock is achieved in under 2 seconds. They aim at where we are. We aim at where they're going to be. Locking on is only the start. A mission kill requires the beam to dwell on a specific vulnerable point long enough for heat to build, penetrate, and cause irreversible damage. For smaller, unarmored threats like quadcopter drones, this can be as little as 2 to 5 seconds with a 30 kilowatt class laser. The earlier LAWS demonstrated this repeatedly against UAVs, melting circuits and triggering catastrophic failures almost instantly. For more resilient targets like small boats with metal hulls or cruise missiles, the dwell time increases. A 60 to 100 plus kilowatt system like Helios can burn through structural material or blind sensors in under 10 seconds for most unarmored vessels. Against hardened or heat-resistant surfaces, a mission kill might take 20 to 30 seconds of continuous dwell, assuming stable tracking. Their defenses buy them seconds. We spend those seconds ensuring their defeat. Atmospheric conditions are the quiet enemy of speed. Water vapor, dust, and sea spray can scatter or weaken the beam, reducing energy on target. In calm, dry air, a high-power laser can achieve full effect quickly, but in heavy humidity or rain, the same system might require extra seconds to compensate. Those seconds can be the difference between a neutralized missile and one that slips through. The physical nature of the target can either speed up or slow down the kill. Reflective coatings or thermal-resistant composites can add precious seconds to the dwell time. In those scenarios, the laser's ability to instantly retarget and keep the beam precisely locked is what keeps it viable. Against drone swarms, the lock and kill cycle repeats in rapid succession. A laser can engage one target, score a mission kill in seconds, and immediately slew to the next without reloading. This demands flawless coordination between sensors and fire control because the window for each engagement shrinks as the swarm approaches. The laser eliminates flight time. There is no ballistic arc, no intercept calculation beyond the beam director's instantaneous aim. The moment a target is in line of sight and within range, the weapon is effectively hitting it. What takes time is sustaining enough energy to cause functional destruction. Real-world demonstrations have validated these timelines. In a US Navy test, a Helios system locked onto a maneuvering drone in under 2 seconds and burned out its sensors in less than 5. A LAWS disabled a fast-moving small boat by focusing on its outboard engine for roughly 15 seconds. These results are repeatable outcomes from operational prototypes. The urgency is not hypothetical. If a sea-skimming missile is spotted only seconds before terminal approach, the laser must lock instantly and achieve a kill in well under 10 seconds. Integration with shipboard radar and early warning systems is critical. Without the earliest possible detection, the laser's speed advantage is wasted. For the crew, the speed of engagement changes the tone of combat. There is no deafening gunfire or missile launch plume, just a silent beam and a target that suddenly fails. This quiet precision is deceptive because it requires an all-or-nothing effort. Maintain the lock and keep the beam on target, because even a momentary break means starting the dwell timer over. In operational planning, the Navy pairs lasers with other defensive layers. Lasers handle close to medium-range threats where their speed and precision shine, while missiles and guns handle longer range or heavily armored threats. This layered approach ensures that if a mission kill is slowed, another weapon system can finish the job. As laser power scales up in future deployments, dwell times will drop further. What takes 20 seconds today might take 5 tomorrow, even against more resilient targets. The clock is always running, and every fraction of a second shaved off is a fraction gained for survival. Modern naval lasers have already proven they can win that race, not in minutes, but in the handful of seconds where combat is decided. On a battlefield where milliseconds decide survival, the most dangerous shot is the one you never see coming. It slips silently across distance at the speed of light, striking not a soldier or a tank, but the enemy's very eyes. A focused laser beam locking onto hostile sensors and optics is not aiming to destroy the whole machine. It is aiming to blind it, to rip away the enemy's ability to see, track, and react. In modern warfare, that can mean the difference between being hunted and being untouchable. The principle is to deny the enemy their vision and strip away their ability to fight effectively. A fighter jet without a targeting pod, a tank with its rangefinder shattered, a warship with its electro-optical trackers dazzled, each becomes a powerful machine reduced to guesswork. They are a powerful machine without perception. That is now our target. Militaries pour research into laser-based counter-sensor technology because lasers rely on precision, control, and the physics of concentrated light, not explosive force or kinetic impact. When a high-energy beam hits an optical sensor, the effect depends on power, wavelength, focus, and exposure time. At the upper end, physical destruction is immediate and irreversible. The laser's photons heat the lens or mirror in microseconds. Delicate coatings burn away, and glass deforms. The heat stresses fracture the material in a pattern called crazing, scattering incoming light and making the sensor blind. If the beam stays on target for even a second longer, the damage can escalate into cracks, melting, and complete failure. The system is permanently crippled without any need for an explosive. Not all strikes aim for such devastation. Sometimes, the mission calls for disruption without destruction, a tactic known as dazzling. Lower energy continuous beams or short intense pulses can saturate a sensor's detector with overpowering light. For a thermal imager, this looks like a whiteout. For a night vision device, it is a bloom of brilliance that erases detail. The effect is temporary but immediate, and while dazzled, the system cannot lock onto targets or guide weapons. Against fast-moving threats, even a few seconds of blindness can break a kill chain. Their sight is a privilege we can revoke at will. The comparison to the human eye is more than a metaphor. Many electro-optical sensors mimic biological vision and are built for sensitivity, not resilience. They are designed to pick up faint heat signatures or a glint of metal in the dark. That very sensitivity makes them susceptible to concentrated energy. It is like a microphone that can hear a whisper, but bursts into static if a firecracker goes off nearby. Once their optics are burned or their image intensifiers fried, repair requires replacing components. The effect of losing these sensors ripples outward. A tank crew deprived of its optics must revert to manual gunnery. A ship whose infrared system is blinded can no longer cue its missile defenses, and a drone with a burned-out camera becomes a blind aircraft. Each of these losses forces commanders to alter plans and accept greater risk. In a fast-moving battle, that loss of momentum can be fatal. Their ability to react is dependent on what they see. We are ensuring they see nothing. Laser attacks on sensors also sidestep some of the political and humanitarian issues tied to kinetic strikes. Knocking out a missile's seeker head with a laser doesn't create shrapnel or blast waves. It can be done silently, invisibly, and without revealing the shooter's position. This stealth makes laser systems attractive for both defensive and preemptive roles. The technology is not theoretical. Field tests and operational deployments have proven it works. The U.S. Navy's optical dazzling interdictor, Navy, Odin, is designed to protect ships by targeting and dazzling hostile optics on drones and small boats. The underlying science is the same. Detect the threat's eye, focus light on it, and overload it until it can no longer function. While lasers are less reliable in bad weather, at tactical distances against exposed optics, even reduced beam power can be enough to dazzle or damage. Advances in adaptive optics and beam control are pushing these limitations back. The psychological impact on the enemy should not be underestimated. Knowing that your sensors could be blinded at any moment changes behavior. Operators might limit sensor exposure or hesitate to scan suspected hostile sectors, all of which reduce situational awareness. That uncertainty creates a constant undercurrent of fear. In a future conflict dominated by autonomous systems, machine vision will be the lifeline of unmanned vehicles. Lasers that can selectively blind these systems offer a way to neutralize threats without costly kinetic exchanges. The battlefield becomes a struggle for sensory dominance. Whoever can see and sense most clearly wins, and whoever loses their vision first is at a profound disadvantage. In a moment, the ship hums with the steady rhythm of engines, lights, and electronics. The next, everything dies. No warning sirens, just a crushing silence. The hum replaced by the eerie absence of power. Darkness swallows the passageways, and consoles go dead. The ship is blind, mute, and adrift. Every crew member feels the weight of the ocean, the realization that they are on a steel island with no propulsion, no navigation, and no eyes. This is not a drill. The immediate reaction is instinctive and trained. The bridge crew snaps to emergency protocols, calling for status reports. Without propulsion, the ship can drift into shoals or enemy waters. The helmsman's controls are dead, so the order is given to shift to manual steering. Lookouts are posted to take visual bearings, and paper charts are opened because GPS and radar screens are black glass. They built a digital ship, and we simply unplugged it. Below decks, engineering teams race toward the problem, like firefighters. Electricians head for the main switchboard, and damage control parties check for fire or flooding. If backup generators are available, they are brought online in a choreographed sequence. The chief engineer directs the isolation of damaged circuits and orders emergency lighting. The captain's mind runs through layers of consequence. Without power, there is no propulsion, no communications, and no weapon systems. The order goes out to prepare anchors for a last line of defense against drifting. Radio calls are made to nearby ships using old-school voice transmission if independent radios still have battery power. The psychological impact is immediate and heavy. Even the most experienced sailors feel their pulse spike. A ship is a complex ecosystem, and when that ecosystem flatlines without warning, the human brain registers it as an existential threat. Training keeps it from boiling into chaos. Leaders move among their people, issuing orders in calm tones. This presence tells the crew that while the ship's systems have failed, the human system is still in control. This is where drills prove their worth. Sailors rehearse total loss of power, instant shift to manual control, and emergency communications. Repetition builds muscle memory so that, in a real crisis, movement is automatic. The saying in the fleet is, you don't rise to the occasion, you fall to your training. Crews that treat drills as an inconvenience learn the hard way that reaction time in the first 60 seconds can determine whether the incident ends in recovery or disaster. The emergency procedures are brutally practical. First, secure the ship. Second, isolate the cause. Third, restore critical systems in order of priority: navigation, communications, propulsion, and safety systems. Redundancy is king. Modern ships are built with multiple power generation options, battery backups, and manual overrides, but redundancy is only useful if the crew knows how to activate and operate it under pressure. They have the equipment, but we can ensure they never get the chance to use it. The human factor is equally critical. Sudden system failures create a spike in cognitive load. Crews that are mentally conditioned to operate in high-stress environments are far less likely to make fatal errors. A ship that has suffered an unanticipated system failure is in a vulnerable posture. In naval contexts, it becomes a target. This vulnerability drives the urgency to regain at least minimal control. The repair effort is a race against time. Engineers strip down panels, trace faults, and swap in spare components. If the root cause is mechanical, the engineering plant may need hours or even days to return to full operation. The crew's strain is both physical and mental. The constant awareness that the ship is crippled gnaws at morale. Leadership becomes a lifeline. When power finally returns, the transition back to normal operations is deliberate, not celebratory. Post-incident debriefs capture lessons learned, feeding back into training cycles. The measure of a crew isn't whether they can prevent every failure, but whether they can meet one head-on and bring the ship back. The silence after the systems die is not just an absence of sound, It is a challenge to prove that even when the ship's mechanical heart stops, its human heart keeps beating. They will not be defeated by technology. They will be defeated by the consequences of its failure. Modern naval lasers are invisible spears of concentrated energy that strike at the speed of light. The traditional defenses navies have relied on for decades are now either useless or severely weakened against them. Take reflective coatings. They are little more than a delay tactic. Modern naval lasers don't operate on a fixed wavelength. They shift frequencies to exploit weaknesses in reflective surfaces. Even at 99% reflectivity, that last 1% of energy is absorbed. And with beams pushing hundreds of kilowatts, that is enough to start molecular damage in seconds. Once the coating degrades, reflectivity plummets, and the laser bites deeper and faster. What was meant to be a shield becomes a thin skin of false security, stripped away under sustained fire. Ablative coatings fare no better. They rely on the idea that the laser will take time to burn through successive layers. But frequency-agile lasers can target materials in a way that defeats their heat-shedding properties. Coatings meant to last minutes have failed in under 30 seconds. Passive armor buys them time, but not survival. Smokescreens and aerosol obscurants have also lost much of their bite. While they could degrade power on target against early laser systems, advanced naval lasers operate at wavelengths that penetrate many common obscurants. Their fire control systems can compensate for beam attenuation in real time. Shipboard weather sensors feed data into the targeting computers, adjusting power output and focus based on wind, humidity, and rain. Your cloud of protective smoke becomes little more than a temporary nuisance. Electronic countermeasures are equally under siege. ECMs can disrupt targeting sensors or spoof rangefinders, but high-energy naval lasers are paired with hardened multi-spectrum tracking arrays that don't depend on a single sensor type. They fuse data from radar, infrared, and electro-optical feeds, so you would have to blind all channels simultaneously to shake their lock. Even then, the laser itself is immune to jamming. It doesn't emit a signal to be blocked. It simply delivers energy to the hull or optics, and no amount of electronic deception will make that beam vanish. Their old rules of engagement have become our new advantages. In an age where seconds can decide the fate of fleets, the ability to neutralize threats at the speed of light is not just an advantage. It is a paradigm shift. And when you strip away the science and the politics, the image that remains is stark. A beam of invisible energy lancing across the waves, and a warship that, moments ago, was a threat, now lying dead in the water, not from the roar of a cannon, but from the quiet hum of directed power. The future of naval dominance may not sound like thunder. It may sound like nothing at all. It happens without warning. 1 second, the ship's world is intact. Radar screens humming, optical feeds clear, the bridge crew scanning horizon and sky. And then, in a flash of focused energy, the eyes of the ship go dark. The sudden blindness isn't just technical, it's visceral. It strikes not at steel, but at the minds of the men and women aboard. In naval warfare, that's where the real damage begins. A ship blinded by a laser dazzling attack isn't simply deprived of sensors. It's stripped of its sense of control, its ability to read the environment, its confidence in its own survival. The ocean is already a place where danger hides in every direction. Take away sight, and it becomes a psychological cage. The first and most immediate effect is the collapse of situational awareness. For a crew at sea, every movement depends on knowing what's out there, where threats are, where allies are, and how to maneuver safely through unpredictable waters. When a directed energy beam burns into optical systems or overwhelms sensor arrays, the picture vanishes. The radar screen may flicker uselessly. The optical feed becomes a white blur. In that moment, the crew isn't just blind to the enemy, they're blind to the world. Their sophisticated radar, tuned to detect the known, was deaf to the inevitable. The disorientation is immediate and profound. Experienced sailors describe it as being cut adrift in a storm without a compass. The brain struggles to reconcile the familiar hum of machinery with the total absence of navigational certainty, and stress levels spike instantly. That stress compounds because the ocean is unforgiving. Without sensor input, every sound, the low thrum of distant engines, the whisper of waves against the hull, becomes suspect. The mind begins to imagine threats where none exist, a primitive survival mechanism triggered by sensory deprivation. Maritime psychology studies show that when critical situational data is removed, cognitive performance can degrade in minutes. Decision-making slows, reactions become erratic. A captain who once commanded with precision may hesitate or overreact, each choice weighed down by the terror of acting blind in hostile waters. Anxiety blooms in the wake of that blindness. The crew knows that at any moment, a threat could be closing in. They cannot see it, cannot track it, cannot respond with the confidence that training normally provides. The helplessness is more than tactical, it's personal. Every sailor understands the stakes at sea. You are surrounded by an environment that will kill you without hesitation if systems fail. Add the awareness that the enemy can take away your eyes at will, and the anxiety becomes a constant hum beneath every action. Sleep suffers, tempers shorten, concentration fractures. This isn't just bad for morale. It erodes the very cohesion a crew needs to function in combat. This is why laser dazzling doesn't need to burn holes through steel to be devastating. It works on the mind. The psychological blow deepens when the crew realizes that this attack involved no warning shots, no visible projectile, no dramatic missile plume. The strike comes from nowhere, intangible, yet precise enough to hit the most valuable sensors. Their confidence, built on layers of reinforced concrete, was a flimsy curtain before the storm. That's when a new fear takes hold, the perception of the enemy's invulnerability. If they can reach out across miles of ocean and blind us without revealing themselves, what else can they do? Confidence in the ship's own defenses begins to crumble. Systems that once felt like shields now feel like brittle illusions. Crews start to believe, not just suspect, that they're up against an opponent who can control the fight without ever exposing themselves to danger. Unlike conventional weapons, a laser dazzling system is nearly invisible. There's no flash of incoming fire, no contrail to follow back to its source. You can't see the weapon that's disabling you. That invisibility breeds paranoia. If the crew doesn't know where the attack came from, then the attack could come from anywhere. It turns every shadow on the horizon into a potential threat. Paranoia is corrosive in confined environments, and a ship at sea is one of the most confined environments imaginable. The longer the blindness lasts, the more the sense of isolation deepens. Even with allied ships nearby, there's a creeping sense of abandonment, an anti-mattering effect, where crew members feel as though they've been left to fend for themselves against an unseen predator. Operational paralysis becomes the final and most dangerous stage. When key systems are blinded, every move risks compounding the problem. Do you advance blindly into potential danger? Do you retreat without knowing what's behind you? Indecision spreads from the bridge down through the ranks. This is not hypothetical. Historical accounts from sudden sensor loss incidents show a sharp increase in errors, near misses, and communication breakdowns in the hours that follow. In combat, those errors can be fatal. Crews begin second-guessing orders, coordination falters. The ship becomes, in effect, a floating target that cannot fully defend itself. The psychological cascade mirrors what happens in certain disaster and combat scenarios, where sensory loss leads to psychological casualties before physical ones. Even if no one is injured in the moment, morale suffers deep wounds. Crew members may begin experiencing acute stress symptoms, rapid heartbeat, sweating, trembling hands. Over time, if the threat of repeated dazzling attacks remains, chronic symptoms set in, hypervigilance, disturbed sleep, heightened irritability. This can spiral into post-traumatic stress responses. In that state, even a false sensor alarm can trigger panic. The strategic brilliance of laser dazzling lies in how it merges technical effect with psychological warfare. The blinding is reversible. The sensors may recover once the beam stops, but the mental impact lingers far longer. The enemy doesn't need to destroy your ship to neutralize it. They only need to convince your crew that they are already defeated. The mountain, once their shield, became a monument to their miscalculation. The fear of the next blinding attack becomes as effective as the attack itself. Every time the crew scans the horizon, they're not just looking for threats, they're waiting for their vision to vanish again. That's why modern naval planners take the psychological impact of directed energy weapons so seriously. It's not enough to harden optics or develop countermeasures. Crews must be trained to operate under sensory loss without succumbing to fear. Because in the moments after a ship is blinded, the real battle is in the minds of the sailors. If they can't maintain cohesion, discipline, and confidence in their ability to fight blind, the enemy has already won the first engagement without firing a single conventional shot. In this way, a focused laser beam becomes more than a tactical tool. It becomes a strategic lever. It doesn't just strip away a ship's ability to see, it strips away the illusion of control that sustains morale at sea. It turns every mile of open water into potential kill space, every minute into a test of nerve. And when a crew begins to believe that they can be rendered powerless at will, their will to fight is the first casualty. That's the true power of being blinded at sea. Not the loss of sight, but the loss of certainty. The ocean is dangerous enough when you can see. When you can't, it becomes a psychological battlefield. And in that fight, the laser has already won. What took them years to bury took seconds to exhume. A naval laser engagement begins in silence. There's no deafening boom, no streak of tracer fire, just an invisible beam reaching out from the warship toward its target. In that instant, the ship is not making a statement of war, but of precision, delivering a targeted pulse of energy that can blind a sensor, heat a metal casing, or fry delicate electronics. It is surgical, clean, and, in naval terms, cheap. But this calm introduction to combat can pivot in seconds into the raw violence of a kinetic strike. Where guns roar and missiles tear through the air, that shift from light to metal is the essence of integrated layered defense at sea. The US Navy and other modern fleets have designed their ships to fight in layers, starting with the least costly, fastest to fire weapons, and escalating only if needed. Lasers fit perfectly at the opening of this sequence. They fire at the speed of light, have virtually unlimited ammunition, so long as the ship's power holds, and can switch targets almost instantly. Against a fast-moving drone or a swarm of small boats, a high-energy laser can deliver a disabling blow in seconds without risking collateral damage from explosive munitions. It's a way to keep threats at bay without expending precious missiles or revealing the ship's full kinetic capabilities too early. We simply ensure they won't fire again. But in combat, time is measured in seconds, and lasers, despite their precision, aren't invincible. A laser might take longer to burn through hardened armor than the available engagement window allows. Atmospheric distortion, rain, sea spray, or even smoke from the target can scatter or weaken the beam. And when the target is a missile closing in at supersonic speed, those seconds matter. If the laser's soft kill or hard kill effect doesn't end the threat immediately, the combat system does not hesitate. It escalates. The situational assessment phase is not a leisurely debate. Sensors, radar, and the ship's combat management computer are tracking the target's range, speed, trajectory, and resilience in real time. If the target shows no signs of being neutralized by the laser, if its heat signature remains strong, if its movement continues unaltered, the system shifts priorities. Operators receive alerts, firing solutions for kinetic weapons are generated, and the engagement enters its second stage. This transition is seamless because modern naval fire control systems are built for it. On platforms equipped with systems like the Mk-38 tactical laser system, the laser and the chain gun share targeting data. The moment the laser fails to produce the desired effect, targeting control passes to the kinetic system without losing lock. This handoff ensures there is no gap for the threat to exploit. The gun opens up, hurling 25mm rounds at the incoming target. Or, if the danger warrants, the ship might jump straight to a missile launch, sending a high-speed interceptor to obliterate the threat. The combined arms effect is where the genius of this approach becomes clear. The laser is not just a prelude, it actively shapes the fight. Against a fast attack craft, a laser might disable sensors or set a fire on deck, slowing the boat's speed or forcing its crew to take evasive action. That momentary hesitation, that fraction of reduced speed or loss of targeting, makes the kinetic follow-up far more effective. Guns have more time to track, missiles have a more predictable target to lock onto. In some cases, the laser's role is psychological as well, demonstrating the ship's ability to inflict damage without warning, sowing uncertainty in the attacker's mind. Behind the scenes, integrated fire control systems knit together radar tracks, electro-optical sensors, infrared cameras, and laser targeting optics. This fused picture allows the ship to coordinate multiple layers of weapons without confusion or redundancy. If a missile is closing in, the system can assign the laser to engage first, then cue a close-in weapon system, CIWS, or missile battery if needed, all while deconflicting firing arcs and maintaining the ship's defensive posture. This integration minimizes the risk of wasted fire and ensures that lethal force is applied only when necessary, but with overwhelming certainty when it is. Real-world examples show how this plays out. The Mk-38 tactical laser system, for instance, pairs a laser with a rapid-fire chain gun on a single mount. An approaching vessel can first be targeted with the laser for a visual warning, literally burning a bright visible spot on its hull or equipment. If the vessel ignores the warning or continues aggressive maneuvers, the gun can engage in under a second, delivering a burst that can disable engines or tear through the hull. On larger combatants, lasers might be paired with missile launchers, creating a defense web that can handle both small, nimble threats and larger, heavily armed attackers. The escalation from laser to kinetic is not just about overcoming technical limits, it's about managing risk in real time. In a modern naval engagement, the cost of inaction is catastrophic. An anti-ship missile that closes the gap could destroy the vessel and kill hundreds of sailors. A swarm of fast boats could breach the defensive perimeter, bringing explosives within lethal range. The layered defense model ensures that the ship never bets everything on one weapon system. Instead, it uses every available tool in a calculated sequence, each one buying time for the next until the threat is gone. Naval commanders value flexibility, and lasers give them that in abundance. In tense situations where an unidentified craft approaches but is not yet confirmed hostile, a laser can be used as a graduated response, disabling optics, causing mechanical failures, or issuing a visible deterrent, without the political and operational cost of firing a missile. But when escalation is unavoidable, the shift to kinetic force is immediate, decisive, and absolute. This process reflects a deeper truth about naval warfare in the 21st century. The sea is an environment of rapid escalation. There's no buffer zone, no safe distance where ships can watch threats develop for hours. Drones, missiles, and fast attack craft close the gap in minutes. Integrated systems that allow a warship to move from non-lethal disruption to full lethal engagement without pause are not luxuries. They are survival tools. From a tactical standpoint, the brilliance lies in speed and adaptability. Lasers handle the cheap, plentiful threats. Kinetic weapons handle the ones that demand brute force. By linking the two through shared targeting and control systems, the warship ensures there is no break in its defensive shield. Even if one layer fails, the next is already firing. The Mountain, once their shield, became a monument to their miscalculation. Because the decision-making is supported by automation, the escalation feels instantaneous to the crew. One moment, a beam of light is tracing across the target. The next, the roar of a chain gun or the flash of a missile launch fills the air. For sailors in the Combat Information Center, this escalation is a controlled chain reaction. They monitor the data feed, verify threat classification, and watch as the engagement shifts from silent precision to explosive force. The transition is measured in seconds, but those seconds are the difference between intercepting an incoming threat at a safe distance and facing a detonation close enough to cripple the ship. In the end, the layered defense system's purpose is not just to destroy threats, it's to ensure the ship can fight the next battle. Lasers conserve ammunition for when it truly counts. Kinetic strikes ensure no threat survives. Together, they form a continuum of force that starts with the quiet burn of light and ends, if necessary, in the deafening impact of steel and explosives. A naval laser engagement escalating into a full kinetic strike is not a failure of the laser. It is the proof of a system designed for survival in the most hostile environment on Earth. It's the recognition that while precision is invaluable, decisive power is sometimes the only language a threat will understand. And in that moment, the warship speaks with every weapon it has, layered, integrated, and unflinching. The U.S. Navy's high-energy laser weapons are built to own those seconds, to end a threat before it ever becomes a kill shot. But paper performance means nothing. What matters is how these systems behave when bolted to a ship's deck, surrounded by salt air, rolling seas, and a constant mix of chaos and precision. That's why the Navy tests its laser weapons not in sterile labs, but under the same brutal conditions where they will one day fight. The first real-world proof came in 2014, when the USS Ponce deployed the ANSEQ-3 laser weapon system, LAWS, into operational service. This wasn't a demonstration for the cameras, it was an extended field test in the Persian Gulf, a region notorious for its heat, humidity, salt-laden air, and unpredictable dust storms. Every factor that can degrade an optical system was present, yet the Navy wanted exactly that. A laser that can perform in perfect weather isn't a weapon. It's a prototype. To be combat-ready, it must work in the worst possible conditions, with crew members moving from drills to live operations without a seam. Testing at sea is designed to push the technology past its breaking points. Targets aren't static, painted-on bullseyes. They're fast-moving, unmanned aerial vehicles, skimming the edge of radar coverage. They're small, agile boats, approaching at speeds designed to exploit the gaps in traditional defenses. They're simulated enemy equipment that might one day carry explosives or surveillance payloads. In testing, the laser must track, lock, and neutralize these threats in seconds. A UAV that's killed is not just an academic success, it's proof that the beam can deliver pinpoint energy at a moving object hundreds of meters away, regardless of the ship's motion or the atmosphere's instability. When the Navy's laser burned out the engine of a fast attack boat during trials, it wasn't just a technical milestone. It was a shift in naval tactics. Unlike missiles, lasers have no travel time. The beam arrives at the speed of light, meaning the time between decision and impact is almost zero. That eliminates the launch signature of a missile, the need to account for trajectory, and the risk of missing due to evasive maneuvers. But it also demands flawless integration with shipboard systems. Fire control, sensors, and power supply all need to work in perfect concert. That's why testing includes full integration with the host vessel's combat management system, not as an accessory, but as a primary defensive option. Environmental testing is relentless. At sea, a laser weapon is not just fighting the enemy, it's fighting the air it passes through. Fog scatters light. Humidity absorbs it. High winds create turbulence that can distort the beam. Salt spray clings to optics and corrodes metal. Dust in certain operating regions can settle into critical systems in minutes. The Navy's trials deliberately operate in these conditions because the weapon's combat value depends on how well it maintains accuracy and power output when the atmosphere is working against it. In the Persian Gulf, LAWS showed it could function in high humidity and heat, but testing also revealed limits. Sandstorms and heavy fog could degrade performance, forcing tactical adjustments. These findings drive both hardware improvements and operational doctrine. The modern wave of laser testing builds on those early lessons. The high-energy laser with integrated optical dazzler and surveillance, Helios, represents the next generation, mounted on advanced destroyers like the USS Preble. Helios isn't just a weapon, it's a sensor system with the ability to track and blind incoming optical systems before they can even target the ship. Its power levels are higher, its integration deeper, and its testing more aggressive. When Helios disabled a drone in a live-fire test, it did so while fully tied into the ship's radar and power systems, validating that the destroyer could fight with traditional and directed energy weapons side by side without overloading critical resources. Testing also addresses the biggest logistical hurdle for shipboard lasers: power. A laser's lethality is directly tied to the energy it can draw and sustain. Unlike missiles, which are expended once launched, lasers rely on the ship's generators, meaning they can, in theory, fire indefinitely as long as there's fuel. But that only works if the system can manage power consumption without starving other critical ship functions. Integration trials measure exactly how the laser interacts with propulsion, radar, and other high-demand systems under combat loads. Power spikes, cooling requirements, and rapid cycling between targets are all part of the evaluation. At-sea deployment is as much about crew readiness as it is about the hardware. The sailors operating these systems are not engineers in lab coats. They're warfighters who must make split-second decisions under pressure. Tests include realistic engagement scenarios where operators transition from simulated tracking to live firing without advance notice. This ensures that, in combat, the laser is not just a piece of gear bolted to the deck, it's a weapon the crew can trust and control intuitively. In some exercises, the Navy uses mixed threat swarms, multiple drones and fast boats, attacking simultaneously from different directions. Lasers are tasked with eliminating specific high-priority targets, while other ship systems engage the rest. This tests both the targeting software's ability to hand off threats and the crew's discipline under layered attack. It also exposes the limitations of current systems, such as how quickly the laser can shift from one target to another, and how well it maintains beam quality across different ranges and angles. The results of these trials feed directly into weapon evolution. If a system struggles in heavy fog, optics might be upgraded or adaptive beam control software introduced. If power draw impacts radar performance, energy management protocols are adjusted. Every weakness revealed at sea is one less surprise in combat. This iterative process, test, adapt, retest, is the Navy's safeguard against deploying weapons that look good on paper, but fail in the fight. There's also the question of survivability. A laser system on a warship must endure constant vibration, temperature swings, and the corrosive effects of salt water over months at sea. It must keep operating after weeks without port maintenance, after storms, and even after battle damage to nearby systems. Tests replicate these realities by running lasers for extended periods, simulating operational tempo over entire deployments rather than just isolated engagements. The psychological factor is impossible to ignore. In an age where adversaries monitor every publicized test, a successful live engagement sends a message far beyond the range of the beam. Footage of a drone disintegrating midair or a boat stopping dead in the water communicates a shift in capability, one where the US Navy can neutralize certain threats silently, instantly, and without depleting missile stocks. That deterrent value is part of why the Navy conducts some tests publicly while others remain classified. The payoff for this exhaustive testing approach is a weapon that changes the economics of naval defense. Missiles are expensive and finite. Lasers cost little per shot once installed, and their magazine is as deep as the ship's fuel reserves. But they are only as valuable as their proven performance under real-world conditions. That's why the Navy refuses to shortcut the process. Deployment aboard active ships, engagement with real targets, environmental stress testing, and full integration trials are mandatory before declaring a laser combat ready. As Helios and its successors continue to undergo operational testing, the Navy is already preparing for larger, more powerful systems that could engage faster, farther, and in worse conditions than ever before. But the core principle will remain the same. No weapon is trusted until it proves itself at sea against real threats in the same chaos where it will one day be called to save lives and ships. In the end, the Navy's testing strategy ensures that when a high-energy laser weapon finally fires in combat, it will not be a gamble. It will be the result of years of deliberate exposure to every variable the ocean can throw at it: salt, heat, wind, rain, dust, and the unpredictability of human conflict. It will be a weapon forged in the only place that matters for a warship, the sea. And when that moment comes, the beam will not just cut through its target, it will cut through decades of doubt, proving that directed energy has a permanent place in the arsenal of naval power. In naval warfare, cost is more than a budget line. It's a strategic weapon in itself. Every engagement choice made at sea balances lethality, speed, and sustainability. For decades, missile interceptors have been the backbone of shipborne defense, capable of destroying incoming threats before they can reach striking distance. But every standard missile, every ESSM launch, carries a price tag that can run into hundreds of thousands or even millions of dollars per shot. In high-intensity scenarios, particularly against swarms of drones or small craft, this becomes not just costly, but unsustainable. This is the problem naval lasers are designed to disrupt, not by replacing missiles entirely, but by absorbing the volume of low-end, short-range, and asymmetric threats that would otherwise drain expensive inventories. A laser's most revolutionary advantage is its cost per shot. It doesn't rely on a warhead, solid fuel booster, or complex guidance package. It draws only the electrical energy stored and generated by the ship's own systems. The US Navy's Helios and the earlier laws have shown that, once installed, each laser engagement costs mere dollars in electricity, even when firing repeatedly. Contrast this with a $1.5 million missile fired at a $2,000 drone, and the imbalance is obvious. The economics alone change the tactical equation. Lasers make it feasible to counter swarms without bankrupting a ship's combat endurance. Missiles also have a physical limit. Every cell in a vertical launch system is precious space. Once those missiles are fired, resupply at sea is complex, slow, and risky. Lasers, on the other hand, have what sailors call a virtually unlimited magazine. As long as the ship has power, the weapon can fire. There's no crane lifting new interceptors onto the deck, no months-long production lag. This perpetual readiness gives commanders confidence in high-volume engagements, knowing they won't burn through critical missile stockpiles when facing dozens of small, agile threats. Speed is another decisive factor. A missile interceptor must detect, track, launch, accelerate, and maneuver to its target. Even the fastest intercepts have time of flight measured in seconds, valuable seconds in which a fast drone or incoming rocket can close distance. A laser beam moves at the speed of light. The moment it's aimed and fired, it begins delivering destructive energy. This allows engagements that are almost instantaneous once the target is tracked, buying precious time in layered defense. Precision is where naval lasers shift from blunt force to surgical strike. They don't need to obliterate a threat with explosive force. They can focus energy to disable optics, sensors, or propulsion systems. In tests, Navy lasers have burned through small boat engines, neutralized drone control systems, and destroyed airborne targets without debris showers that can pose risks to the ship or crew. This precision means less collateral damage and better compliance with rules of engagement in congested waterways. However, the Navy isn't under any illusion that lasers are a silver bullet. Their range is limited compared to missiles, especially in adverse weather or atmospheric conditions where water vapor, dust, or heat shimmer can scatter the beam. They don't yet have the power levels to reliably destroy larger, heavily armored threats at long distances. This is why they're positioned as part of a layered defense strategy, working alongside kinetic interceptors, close-in weapon systems, and electronic warfare measures. Lasers take the inner layer, soaking up short to medium-range threats, so missiles can be preserved for higher-end targets beyond the laser's reach. The age of the laser is here, and, with it, the death of certain comfortable assumptions about naval defense. This layered approach isn't just about conserving missiles, it's about operational sustainability. In a prolonged conflict, missile resupply chains can be disrupted, ports blockaded, or production slowed. A ship relying solely on missiles could find itself empty before the fight is over. By shifting the bulk of small target engagements to lasers, The Navy ensures that expensive missile interceptors are available when they're truly needed. The logistics burden is also reduced. Every missile stored aboard takes up space, adds weight, and requires maintenance. Reducing the consumption rate of interceptors means fewer resupply missions, less vulnerability during replenishment, and more flexibility in loadout. This translates into longer patrols, greater readiness in contested waters, and less dependence on vulnerable supply lines. What makes this shift more urgent is the changing nature of naval threats. In recent years, swarming tactics by small, unmanned aerial systems, fast attack craft, and improvised sea drones have moved from theory to reality. Adversaries are fielding cheap, expendable systems in large numbers precisely to exhaust missile defenses. In such scenarios, every $2,000 drone destroyed by a $2 million missile is a victory for the attacker's strategy. Lasers reverse that equation. They make swarm attacks cost-ineffective for the aggressor. Operational tests back up the theory. The Navy's deployment of Helios aboard Arleigh Burke-class destroyers has demonstrated successful engagements against drones and small boats under various conditions. The earlier LAWS system, deployed on the USS Ponce, provided further proof, disabling targets with repeatable accuracy. These tests have shown that not only can lasers operate at high volume, but they can do so without the wear and tear cycle that limits missile launch systems. In a high-threat environment, this capability translates into constant presence. A missile ship might hesitate to engage every contact, weighing cost and inventory. A laser-equipped ship can respond to repeated provocations without the same financial or logistical hesitation, signaling readiness and control without emptying its magazine. This psychological effect matters. Adversaries quickly assess the cost exchange in a confrontation. When they realize their cheap platforms are being neutralized at negligible cost, the deterrent value multiplies. It changes behavior before escalation, reducing the likelihood that harassment or probing attacks will succeed. Still, missiles retain their irreplaceable role for long-range and heavily defended threats. Anti-ship cruise missiles skimming the horizon, ballistic missiles on terminal approach, or large aircraft. In these engagements, the sheer kinetic and explosive power of a missile remains unmatched. But by offloading the bulk of small, short-range, and repetitive threats onto lasers, the Navy can reserve those missiles for moments when nothing else will do. In essence, naval lasers don't just defend ships, they defend the missile inventory itself. They preserve the Navy's ability to project force deep into a campaign without pausing for resupply. They shift the economics of engagement in favor of the defender, eroding the attacker's cost advantage in asymmetric tactics, and they do it while offering unmatched speed, precision, and endurance in the fight. This isn't a vision of the distant future, it's already happening. With each successful test, each operational deployment, the calculus of naval defense changes. Lasers are proving that they can shoulder the burden of high-frequency engagements, letting missile systems focus on the threats that truly require them. It's a shift that makes fleets not only deadlier, but more resilient, more sustainable, and ultimately more prepared for the long fights modern naval warfare demands. The failure of these traditional countermeasures isn't theoretical. In multiple naval trials, mock threats equipped with reflective surfaces, thermal coatings, and ECM pods were systematically disabled by sustained laser fire. Small drones had their control systems fried in midair despite evasive flight patterns. Speedboats with reflective paint schemes lost their engines after brief bursts. In each case, the pattern repeated. Defenses that might once have worked against a missile or shell did nothing to stop a pinpoint beam of light pouring heat into a single critical spot. Their defenses, once their pride, are now a museum of bad ideas. The reason is simple but decisive. Modern naval lasers combine high energy output with adaptive intelligence. They aren't static weapons firing a single color of light. They're dynamic systems that choose frequency, pulse length, and beam shape based on what they're hitting. They read their targets in real time, exploiting material weaknesses as soon as they're detected. Against that adaptability, any one-size-fits-all passive defense is doomed. Thermal and ceramic coatings, once touted as the future of anti-laser armor, offer some protection against rapid heating, but they're heavy, expensive, and brittle. Against short, low-power pulses, they work. Against sustained, high-energy beams, they crack and spall. The brittleness becomes a fatal flaw. Microfractures propagate under repeated heat stress, creating pathways for the laser to penetrate. In naval combat, every gram matters, and these coatings add significant weight without guaranteeing survival, forcing commanders to weigh their dubious benefits against speed, maneuverability, and fuel efficiency. What about simply moving out of the way? Maneuvering and agility can indeed complicate a laser's aim, but modern naval lasers are built to track with incredible precision. Their gimbaled mounts and computer-stabilized optics can hold a beam on a target across waves, wind, and evasive action. Long-duration tracking and high dwell times mean that even fast-moving drones or missiles can be held in the crosshairs long enough to melt sensors, detonate warheads, or shear control surfaces. For slower, larger targets like ships, evasive maneuvers are almost irrelevant. The laser's line of sight advantage makes it impossible to outrun light. The strategic consequences are profound. Nations that once relied on layered passive defenses, armor, coatings, ECM, are now forced to rethink naval survivability. The only truly effective strategies against modern lasers are active and multi-layered. You must intercept incoming threats before they enter laser range, use decoys to draw fire, deploy your own directed energy weapons in counter-battery roles, and integrate kinetic interceptors to engage platforms carrying lasers. You don't try to block the beam, you prevent it from firing in the first place or overwhelm it with more threats than it can handle at once. There's also a psychological shift underway. Naval warfare has long revolved around the idea of trading blows. Missiles for missiles, guns for guns. Lasers change that equation. They have effectively unlimited ammunition as long as the ship's power holds. They can fire an all-weather short of the most extreme, at virtually no per-shot cost once installed. Against such a weapon, running out the clock or exhausting its magazine, classic tactics against missile-armed ships, simply don't work. This forces both tactical and strategic recalculations, because time now favors the attacker armed with a laser, not the defender relying on traditional shields. In fleet exercises, commanders have learned quickly that their trusted countermeasures are paper tigers in this new environment. A reflective drone that could survive multiple missile hits can be gutted by a laser in under 10 seconds. A fast patrol craft banking on agility can have its sensors burned out before it even completes its first evasive turn. These are not isolated failures. They're consistent results in engagements where lasers are given line of sight. The implications go beyond ship-to-ship combat. Aircraft, satellites, and even ground vehicles equipped with older countermeasure suites are discovering similar vulnerabilities. Naval lasers aren't just naval weapons. Their technology migrates, and once installed on land or airborne platforms, the same countermeasure failures apply. Their confidence, built on layers of reinforced concrete, was a flimsy curtain before the storm. In a future conflict, any platform relying solely on reflective coatings, thermal armor, or ECM without active defenses is signing its own death warrant. All of this underscores a single, urgent truth. There is no silver bullet defense against modern naval lasers. Passive measures alone cannot withstand them. Even layered passive measures crumble when the attacker can adapt beam characteristics and maintain focus on target for as long as needed. The only viable path forward is an adaptive, multi-layered defense that combines movement, active interception, deception, and, increasingly, your own directed energy capability to fight light with light. Imagine standing on the deck of a warship in hostile waters, your radar crowded with fast-moving blips. A swarm of small, fast-attack craft is closing in from multiple directions. Traditional defenses, missiles, autocannons, could destroy them, but at a staggering cost in ammunition and precious seconds. Then with no smoke and no thunder, beams of invisible energy leap from your ship. Engines on incoming boats fail in mid-charge. Sensors on drones go dark. The swarm evaporates. This isn't science fiction anymore. It's the reality the US Navy has been perfecting through years of rigorous exercises and operational tests. The Navy's pursuit of high-energy laser weapons was never about replacing firepower for its own sake. It was about solving a dangerous, escalating problem. In maritime warfare, swarms are the nightmare scenario. Dozens of small, maneuverable threats attacking simultaneously from multiple bearings, overwhelming defensive systems. Adversaries have embraced this tactic because small craft are cheap, fast to build, and deadly when massed together. To counter them with conventional weapons means expending million-dollar missiles on boats that cost a fraction of that and risking running dry before the threat is over. Laser weapons reverse that equation. They offer a virtually bottomless magazine, with each shot costing only the fuel needed to power the beam. The first major proof came in 2014, when the laser weapon system, LAWS, was installed aboard the USS Ponce. Operating in the Persian Gulf, it faced realistic scenarios against simulated fast attack boats. The results were decisive. LAWS could acquire, track, and disable multiple engines in quick succession, using scalable power to tailor the effect. At lower settings, it could blind or disable sensors. At higher power, it could burn through key components and render a craft dead in the water. The crew reported that it worked in all weather conditions encountered, and it was cleared for operational use, the first US Navy shipboard laser weapon to reach that status. Beyond its technical performance, LAWS proved a crucial point. Lasers could sustain multiple rapid engagements without pause for reload. Against swarms, that is the ultimate advantage. As small craft darted in from different directions, the beam director pivoted instantly between targets, each engagement lasting mere seconds. This kind of speed is humanly impossible with traditional weapons that require re-aiming and reloading. The demonstration made clear that a well-integrated laser system could strip a swarm's offensive punch before it even got within weapons range. The next leap forward came with the solid-state laser technology maturation, SSL-TM system, aboard the USS Portland LPD-27. This was not just an upgrade, it was a step toward higher power and precision. In its at-sea tests, SSL-TM took down aerial drones and neutralized small craft with improved beam control. Engineers aim for power levels exceeding 150 kilowatts, enabling faster kills and greater range. These trials were explicitly designed to simulate modern threat environments where a swarm might combine both surface and airborne elements, speedboats rushing in low, while drones provide targeting data or carry explosives. The Portland's tests showed that a single laser system, if sufficiently powerful and well-directed, could handle both threat types without switching weapons or exhausting ammo. By the time the Helios system was fitted to the USS Preble in 2024, the Navy's laser program had matured into a combat-ready capability with integrated optical dazzlers and surveillance functions. Helios was more than a weapon. It was also a sensor able to detect, track, and blind optical systems on drones while maintaining readiness to fire high-energy beams. In tests, it engaged both aerial and surface swarming threats in complex environments like the Red Sea and Gulf of Aden, regions where multiple small boat incidents have challenged naval vessels in recent years. The integration with the Aegis combat system meant Helios could work seamlessly alongside missiles and guns, but reserve its fire for threats best countered with precision and speed. One of the critical enablers of this dominance over swarms is the incorporation of artificial intelligence and automated targeting. A human operator, no matter how skilled, can only process so many targets at once. In a swarm, dozens of contacts might be maneuvering at high speed, changing course unpredictably. AI-driven targeting allows the laser to prioritize threats dynamically, cueing the beam director from one target to the next with minimal delay. It can distinguish between decoys and genuine threats, allocate optimal dwell time for each shot, and keep firing until the swarm is neutralized. The result is a system that can handle saturation attacks without the performance degradation a human crew might suffer under the same pressure. They fired first. We simply ensured they wouldn't fire again. These capabilities don't just neutralize the swarm, they change the psychology of the fight. For the attacker, swarm tactics rely on overwhelming the defender's decision-making and depleting their ammunition. When confronted by a vessel that can strike each unit in the swarm in seconds without running out of shots, the calculus changes. The cost-effectiveness flips. Each attacker destroyed costs the defender almost nothing. This deterrent effect could make adversaries think twice before committing to a swarm assault in the first place. In repeated exercises, the Navy has refined not only the lasers themselves, but the tactics for employing them. This includes integrating them into layered defense systems, using lasers for the first line against small, fast targets, while keeping missiles and guns ready for larger or more distant threats. It also includes training for rapid handover between multiple laser-equipped ships in a formation, allowing one vessel to engage a swarm while others focus on different mission priorities. The logistical advantages are equally important. Traditional missile and gun systems require vast supply chains to maintain readiness. Every shot fired is a round that must be replaced. In forward-deployed environments, resupply can be difficult or dangerous. Lasers bypass that constraint. As long as the ship's power systems are functioning, the weapon remains fully stocked. In protracted engagements or dispersed operations, that endurance can mean the difference between holding the line and being overrun. Real-world operations have underscored the urgency. Incidents involving drone swarms and fast attack craft in maritime choke points have shown how quickly a situation can escalate. The Navy's exercises are not abstract. They are rehearsals for scenarios that have already played out in parts of the world where U.S. vessels operate. The Ladeus trials in the Gulf, the SSL-TM engagements in the Pacific, and the Helios demonstrations in contested waterways all map directly onto threats seen in the headlines. The cost per kill advantage is impossible to ignore. A single anti-ship missile can cost millions. A laser shot is measured in dollars or even cents worth of fuel. Over time, this transforms the economics of naval warfare, allowing high-value ships to defend themselves and their formations against cheap, mass threats without bankrupting their defense budget or risking depletion in combat. Perhaps most importantly, these systems have shown adaptability. Lasers can be tuned, increasing or decreasing power to match the target and the rules of engagement. They can disable without destroying, offering commanders non-lethal options to stop hostile craft without escalation. Or they can apply full power to eliminate a confirmed threat. This precision fits the demands of modern maritime operations, where ships may face both legitimate civilian traffic and hostile actors in the same sea space. From the USS Ponce's early days with LAWS to the USS Preble's cutting-edge Helios, the Navy has built a clear record. High-energy lasers can dominate swarms of small craft in exercises that mimic the speed, unpredictability, and danger of real-world encounters. They have shown that the swarm problem, once a major vulnerability, can be turned into a tactical advantage. With AI integration, endless magazines, and precision engagement, the U.S. Navy's laser arsenal is redefining the defense of the fleet. In the coming years, as power levels climb and targeting systems grow even faster, the gap between ships with lasers and those without will only widen. For adversaries relying on the chaos of swarms, these exercises have delivered a sobering message. The age of overwhelming a U.S. warship with masses of small, cheap craft is ending. The invisible beams that once belonged to science fiction are now cutting through the very tactics designed to exploit naval weaknesses, and they are doing it in silence at the speed of light. The age of the laser is here, and with it, the death of certain comfortable assumptions about naval defense. Ships can no longer count on time-worn tricks to survive the first strike. Coatings will burn, smoke will clear, electronics will be ignored, and speed will only buy seconds. The next era of naval warfare belongs to those who understand that you can't hide from light. You can only outthink it, outpace it, or answer it with your own.